Okay, welcome to part 5 of our video exploration of section 3.4. So just to recap where we are. We've been looking at solving linear systems like this, whoops, y is a vector function, okay, where A is a real valued matrix. But we sometimes find that we get complex eigenvalues, so I'm supposing that for a real valued matrix, we got two complex eigenvalues, alpha plus or minus beta I. So that alpha is the real part, and beta is the imaginary part of those complex eigenvalues. With that, we can build ourselves a complex solution. If we choose V to be a non-zero vector that's an eigenvector, it's redundant to say it's non-zero, if it's an eigenvector that's an eigenvector for one of these, then I can go ahead and build myself a solution. So I'm going to take e to my eigenvalue times t multiplied by an eigenvector. It does not matter here whether I use alpha plus beta I or alpha minus beta I, but whichever one I do choose to use, I'd better make sure that V is an eigenvector for that eigenvalue. Okay. And then we saw I can break that up into the real and imaginary parts, and those were going to be two independent, real valued solutions. Kind of cool. Okay. Now, what we saw in the last video is that this means that the solutions x and y as functions of t were both going to have this form. They were going to be e to the alpha t. That shows up in both of them, where alpha, remember here, is the real part of our complex eigenvalues. And then each was going to be some combinations of sines and cosines of beta of t. And we saw that we could actually rewrite those so that they were both just transformations of the cosine graph. So potentially different transformations. What's the same here is they both involve an e to the alpha t, and beta t shows up as the original sort of theta that we're working with. But the scalar by which we're scaling it could be different for x and y, and what we call the phase lag, the amount that we're shifting things horizontally, could be different for the two. So what I want to do is now take this information and see what that tells us about our phase portrait. So there are basically three possibilities that I've illustrated here. The first is if alpha, which is the real part of our complex eigenvalues, is positive. Now we saw last time that that meant our x and y solution curves as functions of t were going to look something like this. Now I happen to have just graphed one that I'm saying is the x value. The y graph would look very, very similar, because if I'm scaling by e to the alpha t and alpha is positive, then I'm getting a function that's oscillating, but the oscillations are growing in size. So that as t goes off to infinity, the absolute value of x and y is going to be getting bigger and bigger and bigger. Okay. And as t goes off to negative infinity, they're both approaching zero. Okay. All right, that's going to give us a phase portrait that looks something like this. We've got our equilibrium solution at the origin, and all the other solutions are going to spiral away from it. The fact that I've got these trig functions here makes me think of the classic case where x is cosine and y is sine, and I just get the unit circle. Well, it turns out if x and y are both just linear combinations of some sines and some cosines of the same angle, in this case beta t, we're always going to get something roundish. Okay? So something circular or elliptical or spiraling in a circular or elliptical way. Okay. So that part tells me that I've got something roundish. This part tells me that the magnitude is growing, and so we get this that we classify as a spiral source. Case 2, what if alpha is negative, if it's less than 0? Then I'm scaling my cosine graphs by e to a negative power. So both my x and y graphs as functions of t will have oscillations that are decreasing in size as t increases, so that both x and y would be approaching 0. Oh dear, I keep doing this. Sorry, I had that labeled wrong initially. Okay, so then my solution curves will still be spiraling, but they'll be spiraling towards the origin, and in that case we call it a spiral sink. Okay. The third possibility is that alpha could be 0. In that case, e to the alpha t is e to the 0 is just 1. And so we've got our x and y graphs are just oscillating between fixed values. In that case, our solution curves are going to be the equilibrium curve, and then all other solution curves will just be looping around it in a circle or an elliptical path. Okay. So there are a few things that we do need to be on the lookout for. I ended up actually drawing all of these so that they go counterclockwise, but let's not assume that they always do. I could have a solution curve where the rotation is clockwise. That's something that we're going to need to check, and I'll show you how to do that in just a moment. Okay. And also, some of them are more circular looking, and some of them are more elliptical looking. Now, without the aid of technology, I don't expect you to get the shape perfect. I expect you to know whether it's a spiral source, a spiral sink, or a center. I expect you to know whether it's clockwise or counterclockwise, and I'll show you how to know that in a second. And in checking for that, I expect you to respect the information that you gain, which sometimes will inform you as to whether it looks like it's going to be more elliptical or, actually not so much whether it's more elliptical or more circular, but whether it's sort of centered with the axes or whether it's more rotated. You can see this is not aligned with the axes particularly nicely. Okay. So let's just take a look at the original example that we've been working with this whole time, which was y prime equals, and let's see, it was 0, 5, -2, -2. Okay. So we had determined that our eigenvalues were -1 plus or minus 3i. So notice that the real part of that is negative. So my x and y solutions are going to be scaled by a factor of e to the -t. They're going to be approaching 0. So without even finding the general solution, I can actually classify my equilibrium solution. I know my equilibrium solution at the origin is a spiral sink. All the solutions are going to spiral into that. What I don't know is whether they spiral clockwise or counterclockwise. So what I need to do is use the original equation to find the direction of the derivative at some point. Now often the easiest point to plug in is the point just that's 1 unit over on the x-axis. So that would correspond to plugging in 1, 0. If I do that, I'm going to get nothing plus 0 is nothing. -2 plus 0 is -2. Oh my goodness, I just get the first column of my matrix, and that will work every single time. Turns out if you plug in the point 0, 1, you will simply get the second column of your matrix. So what that tells me is that at the point 1, 0, that's the direction of my solution curve that passes through that point. So I've got to be spiraling around the origin, and I've got to be going down as I pass through this point. This one is going clockwise. That's how I know. And so then I just want to draw something so that it's spiraling clockwise away from the origin. Okay. Now, I'm going to erase that because that's not actually part of my solution. That's my phase portrait. So a phase portrait in this case, it's sufficient to just have 2 solutions, the equilibrium solution and 1 representative solution. Not super concerned that you worry too much about whether it's more elliptical or more circular, but you will notice that at this particular point, the tangent vector is straight down. So I respected that vector that I used to get the direction and figure out that this was going clockwise. Okay.